I'm Junki Park, and I'm excited to present our recent work, 3D hand sequence recovery from real blurry images and event stream. This research was a collaborative effort with Jungsik Moon, Weipeng Xu, Evan Caseman, Takaki Shreitori, and my advisor King-Mu Lee. Blur is commonly seen in hand images, as illustrated in the figures below. Due to the fast motion of hands, they often appear blurry, as shown in the figure on the right, highlighting the need for further exploration of recovering 3D hands from these blurred images. However, most previous research has focused on recovering 3D hand models from sharp images, primarily due to the lack of datasets that include both blurry hand images and their corresponding accurate 3D annotations. The primary challenge in creating a blurry hand dataset lies in the reliability of its 3D annotations. As illustrated in the left figure, most markerless 3D hand annotations are generated through a two-stage process. First, multi-view 2D key points are captured, and then these are triangulated into 3D space. However, for blurry hand images, obtaining accurate 2D key points is difficult, making the subsequent triangulation equally problematic. Additionally, blurry hand images present temporal ambiguity, as multiple hand trajectories can result in identical blurry images. For instance, as shown in the right-end figure, both the red and blue arrows represent different hand movements that could produce the same blurred image. To overcome the challenges of acquiring blurry hand datasets with accurate 3D annotation, we introduced the EBH dataset, which captures real motion blur in hand images using cameras with different exposure times. Additionally, we incorporate event streams that record light intensity changes at micro-time intervals, helping to resolve temporal ambiguity. The images below showcase examples from our EBH dataset, including hand images, 3D meshes, and event streams. The figures below outline the process for capturing our EBH dataset. A single camera with extended exposure captures blurry hand images, while 6 additional cameras capture sharp images, 3 triggered simultaneously and 3, with delayed triggers for different time intervals. We also include an event stream in the dataset. The right figure shows the color-coded camera setup. Each blurry image has 6 3D annotations derived from the sharp images. We obtain mono representations by minimizing the loss between 2D joints, rendered silhouettes and masks, and depth maps compared to their ground truth counterparts. Finally, our EBH dataset includes 40,213 annotated blurry hand images from 10 individuals performing various common gestures, along with corresponding event streams. Each blurry image has 6 3D annotations from different time steps, totaling 241,278 3D annotations. Unlike the blur hand dataset, which has minimal blur, EBH features more dynamic blur, as shown in the right graphs. We quantify hand blur by summing distances between 3D key points using ground truth data, reflecting the level of motion blur. To validate the accuracy of our EBH dataset, the table below presents metrics comparing predicted 2D key points, masks, and depth maps to their ground truth counterparts. Predicted 2D key points, masks, and depth maps are derived from 3D meshes, while ground truth data comes from a 2D key point detection model, matting model, and Kinect camera. We calculate the mean distance for 2D key points, IU for masks, and pixel-wise L1 distance for depth maps. Our EBNet first extracts feature in 3 scenarios: image only, event only, and a combination of both. During training and evaluation, we use a temporal splitter with various temporal embedding strategies. Specifically, during training, we apply temporal embeddings when the corresponding ground truth is available. In contrast, during testing, we use new temporal embeddings to generate 3D hand meshes at previously unseen time steps. We evaluate EBNet's ability to generate 3D hands from blurry images by comparing previous deblurring methods. Incorporating a deblurring network before EBNet shows that EBNet outperforms this approach, as deblurring often loses important temporal information needed for accurate 3D hand reconstruction. Unlike deblurring, EBNet effectively uses temporal data to generate 3D hands at multiple time steps. The table also compares our temporal embedding, which concatenates and processes temporal data, with traditional frequency encoding, consistently outperforming it on both blurhand and EBH datasets. Combining images and event streams yields the best results, while events alone degrade performance. The table below evaluates EBNet's ability to generate 3D hands at novel time steps not seen during training. We assess 3D hand recovery for 2 new time steps with EBH, and for the last time step with blurhand, which was trained only on initial and middle time steps. The table compares performance using 3 input combinations and linear interpolation for reference. Linear interpolation, which estimates hands at intermediate times, is less effective than our methods. Our approach, especially with both image and event inputs, significantly outperforms linear interpolation by leveraging temporal embeddings for more accurate predictions. The tables below show that EBNet outperforms previous 3D hand mesh estimation method. Prior approaches fail to address motion blur, leading to inaccuracies. While blurhandnet performs well with 3 specific time steps, it struggles with unseen time steps and lacks temporal consistency. In contrast, EBNet uses comprehensive temporal information and generates 3D hands at novel time steps without needing training data for those specific points. The right table shows that EBNet, especially with both image and event inputs, consistently outperforms previous methods, including event-based ones, and achieves the best results overall. The figure visually compares EBNet with previous methods using image inputs, showing EBNet's superior performance in capturing hand motion and pose. These are the video clips when using different input sources.